Welcome to Mr. Vaughn's classroom. Today we are starting Unit 5, Introduction to Exponential Functions, and we're going to start with Lesson 3, Representing Exponential Growth. If you find these videos helpful, please hit the subscribe button and give this video a thumbs up. Our learning goal today is going to be to explore exponential growth. We have two learning targets in this lesson. Remember to keep these two things at the front of your mind as we go through the practice problems. And if at the end of the lesson you still have questions about either one, please drop a comment below and I'll get back to you with any clarification. Learning target number 1, I can explain the connections between an equation and a graph that represents exponential growth. Learning target number 2, I can write and interpret an equation that represents exponential growth. And we have one glossary term for this lesson: growth factor. In an exponential function, the output is multiplied by the same factor every time the input increases by 1. The multiplier is called the growth factor. So whatever that number is that is being multiplied again and again, such as 2 if you're doubling or 3 if you're tripling every time, that's what we're talking about when we mean growth factor. Now we can begin the practice problems for Unit 5, Lesson 3, Representing Exponential Growth. Our first practice problem asks us, which expression is equal to 4 to the power of 0 times 4 to the power of 2? One thing I want you to know is that when you multiply exponents that have the same base, you add the exponents. Now, what I mean by that is if I have 4 to the power of 0, meaning this little number to the upper right, that is the power. The small number is the exponent, and the big number is what we call the base. So here I am multiplying exponents that have the base of 4. That means 4 to the 0 times 4 to the power of 2 is going to become 4 to the power of 0 plus 2, which equals 4 to the power of 2, or 4 squared. Now the small number to the upper right that we call an exponent tells you how many times to multiply the base number by itself. Therefore, if I have 4 to the power of 2, that means 4 times 4, which equals 16, and that matches choice C. If we wanted to prove this, first we need to understand that anything to the power of 0 equals 1. So if I have 4 to the power of 0 times 4 to the power of 2, then 4 to the power of 0 is 1. 4 to the power of 2 is 4 times 4, which is 16. And 1 times 16 is 16. So this proves that what I said about adding the exponents does in fact get us the right number. If you have any questions about this practice problem, please drop a comment below and I'll get back to you with any clarification that I can offer. Our second practice problem says a bee population is measured each week and the results are plotted on the graph. Number 1, what is the bee population when it is first measured? So for number 1, when it's first measured is going to be the y-intercept. So here we can see that this point is halfway between 0 and 1,000, so the population is 500 bees. Number 2, is the bee population growing by the same factor each week? Explain how you know. So to find out, we're going to divide second y by first y. So that means I'm going to take 1,000 and I'm going to divide it by 500, and that gives me 2. Then I'm going to take the next one, which happens at 2,000, and I'm going to divide it by the previous one, which was 1,000. And that also equals 2. Then I'm going to take the y value at 3 weeks, which is 4,000, and I'm going to divide it by the y value at 2 weeks, which is 2,000. And that equals 2. So the answer is yes. The bee population is doubling each week, or we are multiplying the bee population by 2 each week to get the bee population the following week. And now number 3, what is an equation that models the bee population B W weeks after it is first measured? So what you need to understand for number 3 is that an exponential equation follows the format y equals the initial amount times the growth factor to the power of x. So here, our y is going to be b for bee population. The initial amount we said in number 1 was 500. The growth factor we said in number 2 was 2 because we were doubling. And our input, our x value, is going to be W the weeks after it was first measured. If you wanted to check that, initially would be week 0. Anything to the power of 0 is 1, and 500 times 1 is 500. Next, we had week 1. 2 to the power of 1 is 2. 2 times 500 is 1,000. And that's what we get, 1,000. 2 weeks would be 2 to the power of 2. 2 times 2 is 4, and 4 times 500 is 2,000. And our last point was at 3 weeks. 2 to the power of 3 would be 2 times 2 times 2, which is 8, and 8 times 500 is 4,000, which is what we get. If you have any questions about this practice problem, please drop a comment below, and I'll get back to you with any clarification you might need. Our third practice problem says, a bond is initially bought for $250. It doubles in value every decade. Number 1 wants us to complete the table. So 0 decades since the bond was bought would be the initial value, $250. 1 decade later, it doubles to $500. Another decade later, that 500 doubles to $1,000. And a third decade later, that 1,000 doubles to $2,000. For D decades, we would take the initial amount, 250, we would multiply it by 2 since it was being doubled, and that 2 would be to the power of D, the number of decades. Number 2. How many decades does it take before the bond is worth more than $10,000? Well, if we continued doing this, after 4 decades, that 2,000 would become 4,000. After 5 decades, that 4,000 would double to 8,000. And after 6 decades, that 8,000 would double to 16,000. So it takes 6 decades for the bond to be worth more than $10,000. And number 3, write an equation relating V, the value of the bond, to D, the number of decades since the bond was bought. So if you remember, its output equals initial value times growth factor to the power of the input. So our output for number 3 is going to be V, the value of the bond. The initial value is the $250 initial buying price times the growth factor, which because it's doubling is 2, and our input is D, the number of decades. So that is how we would write the equation for this exponential function. If you have any questions about this practice problem, please drop a comment below and I'll get back to you with any clarification you might need. Our last practice problem says, a sea turtle population, P, is modeled by the equation P equals 400 times 5 over 4 to the power of y, where y is the number of years since the population was first measured. Number 1, how many sea turtles are in the population when it is first measured? Where do you see this in the equation? So you need to remember an exponential equation is output equals initial value times the growth factor to the power of the input. So in this equation, we have P equals 400 times 5 over 4 to the power of y. That means 400 is the initial population. Number 2. Is the population increasing or decreasing? How can you tell from the equation? So, it is increasing if the growth factor is greater than 1. Because I'm getting bigger and bigger and bigger. Multiplying by 1 would leave it alone. It's decreasing if the growth factor is less than 1. So here we need to look at the growth factor and it equals 5 over 4. 5 over 4 can be written as 1.2. This means the population is increasing. Anytime I multiply by a growth factor of more than 1, I am going to increase my output. And number 3, when will the turtle population reach 700? So, after 0 years, my initial population is 400. After 1 year, I'm going to have 400 times 1.2. So I would have 480 after 1 year. After 2 years, I'm going to multiply that 480 by 1.2, and I have 576. After 3 years, I'm going to take that 576 and I'm going to multiply it by 1.2. And I will have 691.2. And finally, after 4 years, I'll multiply that 691 times 1.2, and I'd have 829.44. So it will take 4 years for the population to reach 700. If you have any questions about any of the practice problems that we did in this lesson, please leave a comment below and I'll get back to you with any help I can offer. Before ending this lesson, I want to review our learning targets. If you do not feel comfortable making either of these statements, please leave a comment below asking for help, and I'll get back to you with any clarification I can offer you. Learning target number 1 says I can explain the connections between an equation and a graph that represents exponential growth. Learning target number 2 says I can write and interpret an equation that represents exponential growth. If you found this video helpful, please hit the subscribe button and give this video a thumbs up, and I look forward to seeing you in the next lesson.